Here's an example where we're going to essentially have a balance. It's something that's got two weights suspended on either end, and it's got a fulcrum right in the middle. And the question is, where should the fulcrum be placed so that this thing stays in balance? It doesn't tip over to the left or tip over to the right. The two blocks are hanging from a bar that's 70 centimeters long, and we're going to assume that that bar is massless, so it doesn't contribute to the problem. But the two masses contribute because each are being pulled down. Let's say one weighs 6 kilograms and one weighs 8 kilograms. If they were kind of the same mass, then we kind of have an intuitive sense we should put the fulcrum in the middle. But now the question is, because they're not the same mass and they're going to be pulled differently, where should we put the fulcrum? Well, we're going to split this into two sections. We're going to say one part of this bar has a length x, and that's the one that points over toward the 8 kilogram mass. And we're going to say another part of this bar has a length 70 minus x, 70 centimeters minus x, and that's the one that points over toward the 6 kilogram mass. For this thing to stay in balance, it has to not change an angle. And that means it has to not have an angular acceleration, so it starts to move. To have no angular acceleration, again, means that the sum of the torques is 0. Well, what are the torques? There's a torque pulling on the 6 kilogram mass out at some distance, 70 centimeters minus x, and there's a torque pulling on the 8 kilogram mass at some distance x. Those torques point in opposite directions. The torque numbers that pulling on the 6 kilogram mass, I'm going to leave it to you to assure yourself that you realize that torque is pointing out of the page, that's a vector, and the torque that's pointing on the 8 kilogram mass, well, that's pointing into the page because R points over to the right. The force on that, the gravitational force on that 8 kilogram mass points down. I do my R cross F, and that points into the page. Since they have opposite directions, I'm going to put opposite signs, and I'm going to say T6 minus tau 6 minus tau 8 is equal to 0. So torque is always R cross F, and both angles here are 90 degrees, so that part's easy. But it's now force times distance equals torque. And so that's 6 kilograms times 70 minus x minus 8 kilograms times x. That has to equal 0. So I get 14 kilograms times x equals 420 kilogram centimeters, or x has to equal 30 centimeters. That's the place I should put the fulcrum if I want this thing to stay in balance and not tip. Again, which direction does the 6 kilogram torque point? Well, that's going to point out of the page because, again, torque is R cross F. The radial vector points away from the fulcrum over toward that place where the force is being exerted, so that's to the left. My fingers would then point to the left. And I cross my fingers down because, again, the 6 kilogram force is pointing straight down from gravity, and that's coming out of the screen.